Let's start with the scattering theory. Can you tell me the basics?
Sure. At its core, scattering theory studies how particles or waves interact and deflect off one another. You start with an incoming wave, or particle beam, which encounters some potential or target, causing parts of it to scatter in different directions. The key quantities are things like the scattering amplitude, which describes the probability of scattering at a given angle, and the cross section, which measures the effective area that the target presents to the incoming particles. In quantum mechanics, we solve the Schrodinger equation to find these scattering amplitudes, often using techniques like partial waves or the Born approximation. In short, it's all about understanding how things bounce or spread when they interact.
The key idea is scattering amplitude, and the which describe the probability of scattering at different angle, meaning that if one particle hit another particle, then how we capture that interaction picture that is done by this scattering. And that describes the probability of scattering at given angle, and the cross section which measure the effective area that the target present to the incoming particle. And in quantum mechanics we solve Schrodinger equation to find the scattering amplitude. Other techniques like partial waves or Born approximation, in short, it tells us about understanding how things bounce and spread when they interact.
You've got it. In essence, scattering amplitude gives you the how likely and in what direction for that deflection, while cross section gives you the how big a target does it look like. And yes, Schrodinger's equation, along with clever approximations or expansions, helps us mathematically predict these outcomes. So it's really a framework to model and predict how particles interact.
How particles interact, so meaning that can you explain that how that Schrodinger equation govern that thing?
Absolutely. The Schrodinger equation is like the master rulebook for quantum systems. When you have an incoming particle, the equation describes its wave function, basically a probability wave. As this wave encounters a potential, like another particle or a force field, the equation governs how the wave evolves, whether it bends, spreads, or reflects. By solving the equation with the right boundary conditions, we get the scattering amplitude, telling us the likelihood of different outcomes. In short, the Schrodinger equation dictates how the wave of the particle changes as it interacts, thus predicting the scattering behavior.
Schrodinger equation dictates how the wave of the particle changes as it interacts, thus predicting the scattering behavior by solving equation with the rigid boundary condition. Okay, and which describe its wave function. Okay.
Exactly. The wave function is the central player. It encodes all the possible outcomes. By imposing the right conditions, like how the wave behaves at infinity or near a potential, you extract the meaningful physical predictions like angles, probabilities, and so forth. So it's a beautiful mathematical tool translating interaction into prediction.
Can you give example in the sense when one hydrogen atom interact with another hydrogen atom, their geometry, their scattering theory, and how that interaction picture capture, and how do we translate that information into mathematical picture and predict the solution, that is the scattering amplitude.
When two hydrogen atoms approach, each has a proton and an electron. The interaction is largely governed by the electrons and the repulsive Coulomb forces between the protons. To capture this, we set up the Schrodinger equation with a potential that represents these interactions. The geometry is typically spherical symmetry. By solving the equation, often using partial wave expansions, we get the scattering amplitude. That amplitude tells us, for example, how likely they are to scatter at a particular angle, or even whether they might form a molecule. In short, we translate the physical interaction, two charged particles and their symmetry, into a mathematical potential, solve it, and get predictive scattering data.
So the geometry is typically spherical symmetry. By solving the equation, often use partial wave expansions, we got the scattering amplitude. That amplitude tell us, for example, how likely they are to scatter at a particular angle, or even whether they might form a molecule. In short, we translate the physical interactions to charged particle into their symmetries into a mathematical potential. What was the meaning of that mathematical potential?
That mathematical potential is how we represent the interaction in math form. For two hydrogen atoms, it's often the Coulomb potential, attractive or repulsive depending on particle charges. In other words, it's a function that says, here's the energy landscape these particles feel as they approach or recede. By plugging this potential into the Schrödinger equation, we can calculate how the wave function evolves, leading to predictions of scattering angles or even the formation of a molecule, like H2.
And what's the solution we are getting uh, from that interaction?
The solution is the scattering amplitude. It tells us the probability that the atoms will scatter at each angle. From it, we get measurable outcomes like whether they deflect in certain directions, or if under certain conditions they bind into a molecule. In other words, the mathematical result lets us predict the outcome of the interaction, whether they bounce apart, scatter in specific patterns, or form H2.
So whether they bounce apart, whether they scatter in a specific pattern, or whether they form H2. Okay, what are the essential ingredients required for this interaction? Basically, given the particle, at least two particles should be there so that the interaction should happen. And then given the geometry, we should understand at which geometry, at which specific angle it should interact, and then what are the outcomes, meaning that how we can find the probability density for that.
You've nailed the core ingredients. First, you need at least two particles to interact. Second, the geometry comes from the symmetry, often spherical for atoms, so you can break the interaction into angles. Then you solve the Schrödinger equation with that interaction potential, like the Coulomb potential between charges. Solving it yields the wave function. From that wave function, you extract the probability density. This tells you the likelihood of scattering at different angles or forming a bound state. In short, the probability density is the final key outcome, your prediction.
Okay, what about electron interaction, and where do we capture that interaction, and what geometry we should use?
For electron-electron interactions, we typically rely on the Coulomb potential, which depends on the distance between them. Since electrons have identical charges and repel each other, the potential is inversely proportional to their separation. In many cases, we still use spherical symmetry if the system is atom-like. When solving the Schrödinger equation, we incorporate the electron-electron potential, often a function of their relative coordinates. For multi-electron systems, it gets more complex. Sometimes we use approximations like the Hartree-Fock method. But the key is we still model the interaction potential, solve for the wave function, and from that, get scattering amplitudes or energy states.
So what about this spherical symmetry system that we are taking? Where that system we have to take? It's an arbitrary system, or like
We use spherical symmetry when the underlying physics respects rotational symmetry, like atoms where forces depend only on distance, not direction. It's not arbitrary. If the system has a central potential, like Coulomb or gravitational, spherical symmetry is natural. If the system is different, say a crystal with a lattice, it might have different symmetry, like cylindrical or cubic. So the symmetry depends on the physical setup. Spherical symmetry just suits atoms well.
So can you make conclusion what we have discussed till now, and one key aspect that is very relevant we have the discussion.
In summary, we explored scattering theory as a framework for predicting how particles deflect off one another. The key steps involve identifying interacting particles, using appropriate symmetry, often spherical for atoms, defining the potential, like Coulomb, and solving the Schrödinger equation to get the scattering amplitude. The key takeaway is that the scattering amplitude encodes the probability of different outcomes, whether particles scatter or even bind. That amplitude is our bridge between the physical interaction and what we measure in experiments.
So we only use Schrodinger equation or anything.
The Schrödinger equation is the main tool for non-relativistic quantum scattering, but for high-energy or relativistic cases, we use quantum field theory, like the Dirac equation for electrons or Feynman diagrams and the S matrix for particle physics. So while Schrödinger is essential, advanced interactions sometimes need more sophisticated formalisms.
But the basic idea is only that we need at least two particles to interact, and that there should be some geometry where the interaction happen, and that cross sections with related with the and one how we capture that interaction picture through that I think through the scattering amplitude case.
You've captured the essence. At its core, yes, you need interacting particles, a geometry to understand the angles, and the cross section to measure how likely scattering is. The scattering amplitude is the tool that encodes the likelihood of different outcomes, deflection angles, binding, or scattering patterns. Everything else is just refining the details.
Okay, thank you.